Hello, everyone. This is Anu, and today we're talking about degrees of freedom. So, what degrees of freedom does for us is it allows us to basically tell us if a problem is solvable or not. Not all chemical engineering problems are solvable, at least immediately, either because we don't have enough detail specified, we don't have enough information to solve a problem, or it's overspecified. We have too much information and they conflict with each other, so it doesn't work out. So, the example we're going to do to here is just to give you an intuitive sense of things. Suppose I ask you to solve the equation x plus y equals 20. Of course, we can't do this because there's actually an infinite amount of solutions. We could do 1 plus 19. We could do 2 plus 18. We could do negative 5 plus 25, and so forth, so on and so forth. So there's multiple different solutions to this equation. We actually have an underspecified problem here. Because once you define x, y is set, essentially. So we have one degree of freedom. You can set one of the variables and then the solution becomes defined. Let's take it in the opposite case. Let's say we have three equations. Something like this. Now, if you were to actually try and solve this, you would find that there's actually no solution. And the problem here is we have too many equations. We can't satisfy all three of them at the same time with just two variables. So there's no solution. And then finally, we have the ideal situation. So y equals 20, 2x plus y equals 43, where the number of variables equals the number of equations. And now that we have we can actually solve it. So we can do, okay, y equals 20 minus x, do a substitution there. You get x plus 20 equals 43. So then we get x is equal to 23 and y is equal to negative 3. So this is degrees of freedom. Hopefully this gives you kind of an intuitive sense of what we're trying to do here with degrees of freedom. So now that we have that, let's actually look at how we actually compute degrees of freedom. So the degrees of freedom is equal to the number of unknowns in the problem minus the number of independent equations, and we'll get into a second about what independent means, minus the number of other equations. So basically, like in the above example, it's the number of variables you have minus the number of equations. You want those to be the same. If you have degrees of freedom equals 0, you have a solvable system. In essence, there is one and only one solution to the problem, and you can find it. You can solve it. If you have degrees of freedom less than 0, meaning you have more equations than you have variables or unknowns, you have an overspecified system. So this is the case where we had the three equations, but only x and y. Then, of course, degrees of freedom greater than 0 is underspecified. You have too many unknowns and not enough equations. So in general, you'll find that all your school problems will fall into this first category of degrees of freedom equals 0. Because obviously you have homework problems and they should hopefully be solvable so that you can actually solve stuff. A lot of times in industry, however, you will find problems are underspecified. You will have too many variables, more variables than equations. And so in order to be able to solve it, you'll actually have to make assumptions about the values of certain variables, or say, okay, it's reasonable to assume that the value is this, or we want it to be at this, so we'll set it at this, and slowly knock off your degrees of freedom that way. Okay, and now let's talk about these equations because I kind of broke it down here and I threw out this word independent. What does that mean, right? So when we're talking about it in the terms of chemical engineering, right? What sort of equations do we work with? Well, we know mass and energy balances. So those are types of equations we can use. And we want to do as many independent mass and energy balances as we can. So the question is, is there any dependent equations? Let's see that. So let's suppose I have a system and in goes A, B, and C. Does some things and then out comes A, B, C. Correct? So I can do mass balances on each one of these species. So I can do dA dt equals so forth, and dB dt equals da 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 da, and dC dt equals da 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 da. I can also do a total balance, right? So let's say the total mass is m. I can do dm dt equals dot 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 dot. But the question is, which one of these are independent? Well, A, B, and C are independent of each other, but the mass, or the changing the total mass over time, should just be the sum of all the individual components. So in this case, these three are independent equations. The total mass balance is not independent. It's dependent on each of the individual species balance. So you'll find that, as a general rule of thumb, the number of independent equations is equal to the number of species. Species. There we go. And then lastly, other equations is for other relationships between the variables. So for example, let's say we have the fraction of A and the fraction of B. So we typically denote fractions with X. So perhaps the species balance becomes XA, XB, and XC. One equation that relates all three of these is that the fractions should equal 1. So the sum of all the fractions equals 1. That's an additional equation that we can use to relate the variables and solve for our system. So now that we have that, let's actually put this into practice with a problem. So we have the following system here. And the question is, what is the degrees of freedom here? So as a reminder, degrees of freedom equals numbers of unknowns minus number of independent equations minus number of other equations. So let's actually do this calculation here. So how many unknowns do we have? We have M1, X1C, X2A, X2B, M3, X4B, X4C, M5, and X5C. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 unknowns. Now we need to subtract the number of independent equations. Well, we know that we can create a mass balance for each species. The total mass balance, of course, is dependent, but the number of species should be equal to the number of equations. So we have 3 species, A, B, and C. So therefore, we should have 3 independent equations. And lastly, we need to look at the number of other equations. What other equations can we put in here? And so we might say, okay, well, x1c can be related to 0.03b, right? These fractions must equal, sum must equal 1. So we can see that x1c is equal to 1 minus 0.03. So this is one equation. Another equation we can write is for these two. We know that x2a plus x2b is equal to 1. So those are related. Likewise, we can do an equation here. So we have 0.7 plus x4b plus x4c is equal to 1. And then lastly, 0.6 plus x5c must equal 1. That's 4 equations right there. Is there any other relationships that we could perhaps accomplish here? No, there really isn't. So we have 4 additional equations here. And so we get a positive degrees of freedom equal to 2. So currently this problem is underspecified. We would not be able to solve for all these unknowns. The only way that we could actually solve this problem is if we actually specified some of these values. So perhaps what they might tell you is, okay, we should know what we're putting into our unit. That should be specified. And let's just assume that we want our distillate to be a certain value. Let's say we make this 1,000 and this is 1,000 or something like that. So we specify, okay, we want a distillate. We want 1,000 kg coming of A out of the top. Once we've specified those two variables, now we got rid of those 2 degrees of freedoms, and now we can actually solve the problem. But since we don't have that, we have an unsolvable problem. So this is supposed to be a quick thing where you can just pull this out and actually check and make sure that, hey, do I actually have all the information I need to solve the problem? This is hopefully will be a useful tool that you'll use throughout your chemical engineering journey. Anyways, that's it for this video. I'll see you tomorrow in the next one.